Welcome back to my channel. Prevention is better than cure. Hello everyone. Welcome to this session on synchronization in OpenMP. In this video, we will understand critical atomic barrier ordered and locks with examples. So in parallel programming, like multiple threads runs simultaneously. So when these threads share the data, conflicts, when these conflicts can occur, and how the synchronization helps us to manage these conflicts. So these are the synchronization constructs in OpenMP. Let us understand this mainly. In parallel programming, multiple threads executes a task at the same time to improve the performance and execution and reduces the execution time. So, but these threads often operate on shared data or and resources, and which can lead to unexpected issues if not handled properly. So in parallel programming, multiple threads executes a task at the same time to improve performance and reduce execution time. These threads often operate on shared data or resources, which can lead to unexpected issues if not handled properly. So when two or more threads try to read and write the same data simultaneously, it can cause the problems such as race condition, that means incorrect or unpredictable results, data inconsistency, unexpected program behavior. So let us understand that is to prevent these issues, synchronization mechanisms are used. Synchronization ensures that only one thread accesses a critical section at a time. Operations on shared data are performed in controlled and orderly manner. Program results remains the correct and reliable. The common synchronization techniques includes critical like locks, that is a mutex, barriers, critical section, atomic operations. So synchronization is essential in parallel programming to maintain the data integrity, avoid conflicts, and ensure the correct execution when multiple threads share the resources. So let us understand why like this synchronization. So the parallel threads share the data and which needs the coordination to avoid the conflicts. And why the synchronization? That is a basic question we need to ask ourselves to before we proceed to the next. That is to discuss about the different constructs used in this synchronization. So synchronization is a mechanism that is in parallel programming. Uh, Multiple threads often run at the same time and may need to access the shared data or the resources such as variables, files, or memory. So without proper control, this simultaneous access can lead to conflicts or incorrect updates and unpredictable outcomes. So synchronization is the process of coordinating these threads so that the shared resources are accessed in a safe and organized manner. So mainly it ensures that only one thread executes a critical section at a time if required. Operations are performed in the correct sequence. Data remains consistent and accurate. For example, if multiple threads to try to update a bank balance at the same time. So synchronization ensures that each update happens one after the another, so that is to prevent the errors. So common synchronization techniques include the mutex or the locks, and these are mainly to restrict access to the one thread at a time. Next are critical sections like define the protected code blocks, barriers, synchronized threads at a central point, and also the atomic operations, which are mainly used to perform the operations individual. So the synchronization is essential to ensure that the parallel programs produce the reliable, consistent, and predictable results, even when multiple threads operates concurrently. And if you look at the types of synchronizations, OpenMP mainly provides the several synchronization constructs. So the critical construct ensures that only the one thread at a time that executes a block of code, and this is used to protect the shared resources. It prevents the race conditions, like this is mainly suitable for the complex operations involving multiple statements. And then atomic construct is used for simple operations like increment or update on shared variables. And this is faster than the critical and ensures the operations is performed without interruption. This is best for the single and the simple updates. So next construct is barrier. A barrier forces all threads to wait until every thread reaches a certain point, which ensures the synchronization at a specific stage. This is mainly useful when the next step depends on completion of all the threads. Next one is ordered construct. This ordered construct ensures that a section of code inside a loop executes in the original sequential order, which is mainly used to maintain the order while still allowing the parallel execution. And this is used when order or execution matters. Next one is the locks. This locks provides explicit control over access to the shared resources. So threads must acquire a lock before accessing data and must release the lock after use. And this offers the flexible but more complex control. So synchronization constructs an OpenMP is designed for a specific scenario, that is helping to maintain the data consistency, avoid conflicts, and ensure the correct execution in parallel programs. And if you look at the critical section in detail, like a critical section is part of the program where the shared resources like variables or the data structures are accessed or modified. That is mainly to prevent the conflicts such as race conditions. OpenMP provides the critical construct, that is to avoid these race conditions. When a thread ensures the critical section enters into the critical section, it gets exclusive access to that block of code. So no other thread can enter the same section simultaneously. So other threads are forced to wait or blocked until the current thread exits. So this ensures that the data updates happen safely and correctly, and shared resources are not corrupted, and the program results remain consistent and predictable. For example, if multiple threads updating a shared counter using a critical section, that critical section ensures that each update happens one after the another, that is to avoid the incorrect values. So while critical sections ensure the safety, excessive use can reduce the parallel performance due to the waiting time. The critical section is essential for protecting the shared data, ensuring that only the one thread executes sensitive code at a time, and thereby maintaining the correctness in parallel programs. And if you look at the critical section example code, there's the counter, that is the variable that will be updated by the threads. And this every thread will enter into this critical section. Like entry section, and once it enters into the critical section, and then it will access the shared resources, and after using this shared resources, it will exit from the critical section, exit section, and then it will continue in the remainder section. Like next construct is atomic. And this atomic uh, an atomic operation ensures that a simple operation on a shared variable is executed without interruption. So this means once a thread starts the operation, no other thread can interfere until it's complete. Atomic is typically used for the operations like incrementing or decrementing a variable like x plus plus x minus minus, or updating a value x equal to some x plus value, and the simple read, modify, write operations. So why the atomic is faster? So in this case here, this mainly due to because of lower overhead compared to the critical section. The no need to lock an entire block of the code in this atomic, and it uses the hardware level support for synchronization. So only the specific operation is protected, not the whole code block. And if you compare the atomic and this is how the atomic code, the simple code would look like. And before, let us just compare how what is the difference between the atomic and the critical. The atomic is mainly best for the simple single line updates, whereas the critical used for the complex operations involving multiple statements. And if you look at the limitations with and these cannot be used for the multiple statements or the complex logic, and mainly limited to the specific types of operations. So atomic operations provide a fast and efficient way to ensure the thread safety for simple updates, making them a preferred choice over the critical sections when applicable. And next one is a barrier. And this is mainly useful when we need all the threads to complete one phase before starting another. And this is a way we can use this barrier construct like a pragma OMP barrier. So next one is ordered construct. And this ordered construct so critical is more flexible but slower. Atomic is faster but supports the limited operations. So critical is more flexible and this limited operation. So like for example, if you uh, just look little deeper, the critical construct about critical and the atomic construct. The critical construct allows only one thread at a time to execute a block of code, and it can handle the multiple statements and complex logic, and it provides a high flexibility, but it is slower due to the locking and synchronization overhead, and best when operations involve the multiple steps or the complex updates. And if you look at this atomic, this ensures the single operations executes without interruption. It works at a fine-grained level, that is at a single statement. It's much faster than the critical section, but limited to the simple operations like increment and update. So the best for simple read, modify, write operations. So use the critical when the flexibility is required for complex tasks, and use atomic when you need a fast, efficient synchronization for simple operations. And what is the importance of a barrier? This is the synchronization phases of execution. A barrier is a synchronization mechanism that forces all threads in a parallel program to wait at a specific point until every thread reaches that point. Only after all threads arrive at the barrier can execution continues. So why the barriers are important? Mainly because of the phase synchronization, data consistency, coordination among the threads. So the phase synchronization would be achieved, that is mainly to ensure that the all threads complete one phase of computation before moving to the next. This is mainly useful in multi-stage algorithms. Next, data consistency, which guarantees that all updates to the shared data are completed before the next stage begins, so which prevents the incorrect or partial results. And coordination among the threads, they keep the threads aligned and synchronized, avoiding which avoids the mismatches in execution flows. And for example, if you take in a program with the two steps like a compute values and use the computed values, so a barrier ensures that the step 2 starts only after all the threads finish the step 1. So excessive use of barriers can use the waiting delays, so and reduce the performance. So barriers are essential for maintaining the order, consistency, and coordination in parallel programs by ensuring that all the threads move forward together in synchronized phases. And let us look at the advantages here. This synchronization prevents the race conditions, ensures correctness, and maintains the consistency. And if you look at the disadvantages with this, like too much synchronization reduces the performance and limit the parallelism. So the frequent use of synchronization like logs, critical sections, barriers, which this causes the threads to wait for each other, leading to the delays. So increased waiting time, higher execution overhead. So the overall program becomes very slow. And next one is a limited parallelism. That is the main goal of a parallel programming is to run the task simultaneously, but excessive synchronization like forces the threads to execute sequentially in many parts, reduce the benefit of using multiple cores. So parallelism is restricted. So contention and bottlenecks, well, like when the many threads try to access the same synchronized sections, so that creates a contention for the resources, and which forms a bottleneck that slows down the entire system. And complexity in design, like overusing synchronization makes the programs like harder to design and debug, and more prone to the issues like deadlocks and starvations. And if you look at the applications of this, like mainly the banking system, simulation, scientific simulations, and data processing. If you take the banking system, here the synchronization ensure the safe and accurate transactions. Like this prevents the multiple withdrawals from the same account at the same time, maintains correct account balances, which avoids the financial inconsistencies and the fraud. Next one is simulation. So these are scientific simulations used in a mainly used in scientific and engineering simulations, and that is mainly to coordinate the multiple threads working on the different parts of a model, so that ensures the results are accurate and consistent. And this is very important in weather prediction and physics simulations, etc. And if you take another operating system like operating system, So synchronization is essential for processes and thread management, like control access to the shared resources like memory and files, which prevents issues like deadlocks and race conditions, ensures the smooth and stable system performance. And for mainly data processing, like in big data and analytics, synchronization tasks and the parallel data pipelines can be used and maintains the data integrity during the concurrent processing. So that enables efficient handling of a large scale data. So synchronization plays a crucial role in ensuring the correctness, completeness, consistency, and reliability across the various real-world applications where multiple processes or threads operate concurrently.